Okay, Itai, thank you for the introduction. Everyone, welcome. It's great to be here. So to get started here, just a little bit about myself. As Itai mentioned, I solve big data and enterprise AI ML problems at scale. My area of focus here in terms of diving deep on generative AI is what can we build with this technology today, right? I like to liken it to there are a lot of people, particularly researchers, that are out there that are looking at how do I build the next biggest, largest, fastest model, right? I think of that as being similar to building an oven or a microwave. I'm interested in making tasty meals, right? I want to take that technology and do something with it today. So feel free to take a screenshot of this. I'll have this up at the very end as well. Do reach out. I'd love to connect. So my contact info is here. So this project, the motivation of this project came out of work that was done by Simon Willison and Drew Brunig. If you guys are familiar with Simon Willison, Simon was he was one of the founders of the Django Python framework, and most recently has been working on a project called Dataset, which I used as the basis for this project. So Simon's a thought leader in the LLM space in general. He gave a talk last fall at PyBay in 2023. Part of that talk was around embeddings, and there were portions of it that really resonated with me, and I picked up what he had done and really just kind of ran with it, right? So that's where we are today. So starting point, can I see by a show of hands how many people know about embeddings? Okay, so yeah, this is old hat, right? So embeddings, 10 years ago, Google came out with a paper called Word to Vec, which was this idea that you could take text and model it into embedding space, where embedding space is really, it's multi-dimensional space representing a location is what I've got it described as, but really it's an array of floating point numbers. So why does this matter? Is that people use embeddings for things like similarity search, retrieval augmented generation, and clustering. So we'll talk about this more at the very end, but one of the ways that people are getting around fundamental challenges with LLMs, specifically hallucinations and recency, is by using techniques like retrieval augmented generation. And that technique, which is put things in embedding space, find things that are similar, that's exactly what I'm showing here. I just happen to be using images. So what did I do? What I did was I said, okay, I'm first going to download 30,000 pairs of images, or sorry, 30,000 images of eyeglasses. Right. So I went to Glasses USA, I scraped their site, downloaded 30,000 pairs of images locally. I then took the clip model from OpenAI and I said, let me run each of these images as binary data through the clip model and get an embedding. I stored that embedding in a database, in a SQLite database using this dataset framework I was talking about. Then I built 2 pages. Let's actually show it. I'm going to jump over here. I'm going to show it here. So what I did was I built 2 pages. One of them is, here's just a list of random, it's 9 random pairs of images, or sorry, it's 9 random pairs of glasses from that data set. All right. Do you want to pick? So pick a pair that looks interesting.
I like those big black ones.
You like this? You like the Muse X Hillary Duff Lily Shiny?
Yeah. Sure.
Right. So you can take a look at these glasses here. Then if you click on Find Similar, the second page, what it does is it says, let me look up the embedding and then use the Facebook AI similarity search library to find other embeddings that are similar, and then those end up being your similar glasses. Right? So this is the result. Here's the glasses, and here are the similar pairs. How do we do? Pretty good, huh? Pretty good. Yeah, so again, this is using something called FAISS, which is the Facebook AI Similarity Search Library, and it's calculating it based on Euclidean distance. So in here, I've got the distance, it's 2.39, 2.49, et cetera. So we can then, take a look at a different example and say, oh, okay, well, what about this pair here? Let me find similar, and you get not surprisingly, a very similar story of oh, wait a second, I'm finding glasses that are similar to the original pair. So that's the heart of this project. It's really around theme and variation. So if that is the theme, using embeddings to find things that are similar, let's walk through some of the variations that I looked at. So one of the variations I looked at was I said, let me use principal component analysis to reduce down the dimensionality of this 512 element array of floating point numbers, right? So using principal component analysis, I was able to take, if I reduce it down to the first 10 dimensions, that covers 70% of the variability. And what you see there, and let me show this. If I bring this up, now what I've done is on an XY plot, I plotted those 2 dimensions that we were talking about. So I like to refer to this graph as, to me, it looks like, either looks like lungs or kidneys, right? Each one of the markings here represents a pair of glasses. And what you're seeing in terms of XY value, that is the principal component analysis reduced dimension. So dimension 1 and dimension 2. So let's play a little game. As we're going along the right-hand side, can anyone tell me what the glasses in the right lung have in common? I heard it. Yeah, sunglasses. What about the left lung? Yeah, the left lung. So in terms of clustering and sorting, the right lung ends up being sunglasses. The left lung ends up being non-sunglasses, right? Pretty neat.
What's
pretty
in the middle?
cool. What's that?
It's in the middle.
What's in the middle? Well, that's a good question, right? What is between sunglasses and non-sunglasses? So this is a pair of glasses that seem to have a band in the back that's partially obscuring, right? That's just one random one. Maybe I got lucky in terms of hitting that space in the middle. Yeah, I think I just got exceptionally lucky in terms of picking things. But let's continue to explore that concept as we keep going.
What is, if I can ask a question, what is what is towards is there any significance to the models towards the top of that lung versus the bottom of the lung? Do they share any similarity?
So hold that question. We're going to look at that in more detail. I could sort of mouse over and we could try to figure it out ourselves. Actually, let's do that. I'm not going to give you the answer, but I'm going to mouse over a few of these and you can tell me if you see anything, right? So you can kind of look at these over here and you can look at these over here, right? But that was one of the questions that I was trying to say, oh, can I figure it out, right? You seemed like from your reaction, maybe you got it. But we'll come back to that in a second. Sorry, go ahead.
It seems like the color gets the biggest weight here, not the shape, right?
So I'm not sure, right? This is one of the fun things about this is so you're going to the embedding model, then from embedding model to principal component analysis, which is identifying biggest areas of variation. The first dimension, as we identified, was sunglasses versus not sunglasses. Now the question is, well, what is dimension 2, 3, 4, 5? So let's keep going. Let's hold that thought for now, and let's keep going. Next, what I did was I said, what I wanted to do was I wanted to say, okay, well, if the concept of you have a pair of glasses you like, let me find things that are similar to it. If that makes sense and is extraordinarily effective, what about the following idea? And the idea was, imagine there are 2 pairs that you like, right? So if there's 2 pairs you like, and what I did was I built 2 pages. One of them is pick one of 9 pairs of glasses. Right. So what this, oh, sorry, I clicked in the wrong spot. Give me a second. So this here, right. So what this is showing is here are 9 pairs of glasses where you've got pair 1, pair 2. Does anyone have a combination they think is interesting? Call it out.
The third one.
The third one, what, on the first row?
Yeah.
So this one here, these guys here. Okay, so before I click on blend, let me explain what this does, right? It says, I've got my hero pair 1, my hero pair 2. It's going to, in embedding space, find the embedding for pair 1 and for pair 2, then draw a line segment between the 2, chop that line segment up in terms of 20% increments, and then what you have is something that looks, but chop it up in terms of 20% increments, and then at each increment, find the nearest neighbors, find the ones that are closest to that 20%, 40%, 60% point. So I was kind of blown away by this once I got this up and running. So you've got pair 1 on the left, pair 2 on the right. The way to read this is the furthest left column. These are the glasses that are most similar to pair 1. These are the glasses that are most similar to pair 2. With me so far? Then this 80, 20, 60, 40, etc. What this is saying is between these two embedding points, walk 40% of the way, find the glasses that are similar, that are 40%, find the glasses that are closest to that 40% part, right? So let's take a closer look at these two pairs here, right? As you look at this, one of the things you'll notice is you start to pick up like a little bit chunkier of a, does it start to pick up a little bit of the features that you have on the thing on the right-hand side? Those two glasses are actually, to me, seem super close. I'm gonna pick another pair here. Right. So in this case, what you're looking at here is you've got something that's super chunky and sunglasses. Then you've got something that's kind of curved and styled here. In between, these are the glasses that are kind of 60-40 blend. I've been looking at this data a lot, probably looking at something like 100 to 200 of these blends. These are actually the two worst examples I've ever seen. So I'm looking at this going, wait a second, I'm not really, in terms of telling a story around it, it's not as strong of a story as it typically is. And I'm kind of curious about that. So here, for example, right, this is kind of a reasonable story here, where when you look at this, notice the way the bridge on the nose is here versus on the pink glasses. And then if you look at this one, even though you're 60% of the thing on the left, you still kind of pick up the bridge from the thing on the right. Right. So yeah. So again, it ends up being this kind of weird, oddly effective blend of the two. Of okay, I've got two different pairs. Let me really examine the space in between from an embedding perspective. Question.
So you mentioned this this multi-dimensional kind of line be from one to the other.
Yeah.
Okay. Is there a way to control the path of that line? Like let's say I want the blend, that range of glasses, but I want all the glasses that have a certain trait fixed, like I want the most weight to go towards the bridge of the nose, the shape of that thing.
So the way it is right now, it's purely the two pieces in space and then find something in between. One of the later variations is a concept called the equalizer, which if you think about a musical equalizer where you can like raise and lower different aspects, we'll get to that shortly. It's kind of in the same ballpark of what you're describing. So this is what blend ends up looking like, right? Which the two examples we happen to choose aside, I found this to be kind of a remarkably effective way to get at things that are vibes similar to two different pairs. Yeah.
So regarding the embeddings, those
Yes.
were the ones you got from Clip, is that?
Yes. Yeah. All of the embeddings I'm using here, I just ran this through OpenAI's Clip model.
I see.
Yep.
And so in the interpolation, did you are all the embeddings equal length? Or?
Yeah. So Clip will give you a 512 dimensional floating point array, and all of them are 512. So then to get the midpoint between two arrays, between two embeddings, you just say, floating point number, add, divide by 2, right? And just go from there.
Yeah. So like linear. So there's this thing called spherical interpolation.
Okay.
So basically, you have the Euclidean length.
Yep.
One vector.
Yep. Mm-hmm.
If all the embeddings have the same length, then
Okay.
you probably want to, after you do the midpoint thing, probably want to divide by the length, make it unit length.
Oh, okay.
I mean,
Oh, no, I'll take a look at that. Yeah, thank you.
Sorry to interrupt, but I think what he's talking about is normalizing the values in the 512 array.
Yeah.
So I think
Okay.
When you put it into the model, does it normalize the values for the entire array?
I don't know the answer to the question. I'm not sure. The values, so coming out of clip, the values do range from 1 to -1, so I'm assuming that is. When you run it through principal component analysis, the numbers range kind of from the 3.5 to 4 to -4 as well.
And sorry, one last.
Yeah. Go ahead.
Like these images seem to be very small, right? What would happen if you do pixel level PCA?
So these images are only small because I happen to make them smaller to put them on the screen. They're actually much larger pictures. Yeah, I mean, they're not like crazy large, right? But they're, yeah, they're larger. Yeah, they're a little larger. Yep. So next, so if those are kind of the main things that we're looking at, from here I was doing some additional variations. One of the variations was saying, let me try to take similarity search and visualize it, right? So what I did was I said, take the embeddings, run them through principal component analysis to get down to 10 dimensions. Then what I'm going to do is I won't forget to track my time. Okay, for each of the 10 dimensions, I'm going to, so how can I visualize the embeddings? I modified step 1 by saying, let me display a color histogram for the first 10 PCA reduced dimensions. And that color histogram is, the legend is, a large negative number is dark purple, a large positive number is white, right? So what you can see here, and why don't I'll actually just do this live. So for this, if I go here and go to similarity search, so what you can see, it's a little washed out on the monitor, but and if I mouse over, you can see here's the value, right? So this is -0.31 here because it's whiter. This is 2.79. Notice that these glasses are all random, and notice that the histogram, these different colors are all kind of all over the place. If I pick a pair and then look at it, notice that the glasses are similar. The L2 Euclidean scores are really low. And if I look at any given column, right, all the columns kind of line up as well. So again, this is the same thing we were doing in the very first example. It just happens that now I'm using this as a visualization technique, right? So you can see here, here are some other examples as well, right? So if the first dimension is high or the first dimension is low, this is what it ends up looking like. I then did the same thing for the blend example, where you've got pair 1 at the top, pair 2 at the bottom, and then blending in between. The observation here is, wait a second, you go from light to dark or you go from dark to light, right? So again, it's a way to kind of make sense of, hey, what's going on in this weird, wacky world? Question?
So for this blending,
yes.
At each point, you're not calculating a new point and then inverting the embedding to produce a genuine new image. You're just looking for the closest existing ones.
Correct. Yeah, that's actually a really good point. And when I talk about this, I usually mention it. One of the gags that you'll hear about on late night talk shows is, hey, what if these 2 celebrities had a baby, right? And they show blended features. It's not that at all, right? What this is doing is this is saying, here's a point in embedding space, here's a point in embedding space. Let me use that to get a new point in an embedding space and then find things that are similar to that. So what it's finding are actual real pairs of glasses, right? So for me, that's the power of this. This is not just some like party trick where you're, oh, okay, let me Photoshop and take a little of this and take a little of that. It's actually using embeddings to derive, oh wow, here's a pair of glasses that, oh, it's bigger and it's sunglasses, but it kind of has a vibe of that one, and yeah.
Do you use like a GAN applied to that middle point and from the vector embedding generate that image?
I don't know. I don't know if anyone here knows the answer to that.
So I think yeah, that's an interesting question. You
Okay.
can actually probably do that to some extent. Like basically, clip is trained simultaneously with language and images.
Yeah.
So, for example, if you wanted to increase the bridge, like one was one of the comments, you could get the text embedding of that particular, say, a sunglasses with more of bridge or more prominent bridge or something like that, and get the encoding of that one, and then somehow get a prompt for DALI or some kind of model like that, which will take the text and make a image. So it's an interesting experiment.
Right. So the very last thing we'll show here is talking about combining text and images. Yeah, I've got more to say about that. I'll actually hold that for now. In terms of additional variations here, number 5, I was trying to explore the scatter plot edges of, remember the question was, hey, if you're like the things at the top and the things at the bottom, can I tell what these different dimensions mean, right? So for dimension 1, I have it as a positive X value is sunglasses and negative X value is regular glasses. Through my kind of playing around with it, what I found is the glasses that are near the top of the lungs have black frames, and the ones at the bottom of the lungs have non-black frames, right? That's what I did as number 5. Number 6, I said, let me take that same scatter plot idea and let me just take a subset of the 30,000 images. I nearly did it with all of them, but I said, let me do it with a subset. I picked 200 of the images and I said, let me chart those, right? So you can see here, it's the same lung shape, but now you can really start to tease this apart of, yeah, clearly sunglasses, clearly non-sunglasses, etc. Question.
When you were getting the subset, did you randomly sample or was there any criteria?
This is full on random sampling. Yeah. So when I hooked this up, I said just grab 200 at random, and that's what this looks like.
So how did you identify the black?
Trial and error. I just looked at it a bunch, right? Yeah.
So the PCA did not help in any way.
Well, the PCA got me into, now I can look at, here's the second dimension, right? Then I was playing around with this. Another thing, yeah. So, yeah. Next, so the next thing we're getting near the end here in terms of different variations. The next thing I said was, okay, so this is really interesting that you can find things that are related, but imagine a use case that says, I love this pair of glasses. This pair of glasses is great, but it's $244. I don't want to pay that much, right? So are there other glasses that are similar, but don't cost as much? So what I did was I said, okay, great. I can build a graph. Let me put the x-axis is similarity. So this is Euclidean distance. Y-axis is price. So what does that look like? That looks like, okay, here's a pair of glasses at 240. These are all the similar glasses, and the cheaper similar glasses, hey, maybe you should look at these. Yeah.
In lines of this, you mentioned that they want to look at cheaper glasses.
Yeah.
You could probably plot it out and get the cheaper glasses.
Yep.
But what if you were to make this recommendation collaborative? For example, if you use the particular user's previous data of, say, he liked XYZ glasses before this, and he did not like these. So could you use that information to enrich the recommendations the system provides?
So I would say yes, that's certainly something that you can do. One of the key things in all of this is typically systems like this that allow you to narrow down make heavy use of facets, right? So there's metadata that then provides, is this a sunglass or non-sunglasses? What's the color? What's the manufacturer, et cetera, right? And I'm thinking about your question in the context of, hey, did someone like it or didn't like it? Those are effectively facets as well, right? So you could incorporate this as part of a faceting system as well, right? So, oh, there's 3 million glasses here. Let me use facets to narrow it down partially, and then I can use embeddings to go even further, right? Yeah, there's nothing that restricts that, right? So here's what this looks like live. This is a pair of glasses, and then this is, price plot for it, right? So you say like, oh, okay, well, yeah, those are roughly similar. I'm willing to give up a fair amount of similarity to get something that's, a quarter of the price. Okay. Any questions on that one? now, this one is equalizer. So what I did here was I said, okay, so we're playing around with embeddings, and here are these 10 different dimensions. And imagine I kind of go in and say, let me modify these a little bit, you know, a little up, a little down. Now let me find a pair of glasses. This is my selection, and then here are the glasses that are most similar to that, right? Okay, well that's good, but let me modify this a little bit that way. Okay, let me find other ones, right? So now this pops to the top. You know, let me make a big adjustment on this guy, right? Find similar. So that's kind of what this one looks like, right? Which is, hey, you know, play around from an equalizer perspective and see where you land. Yeah.
Would you say that using PCA, yes, it reduces dimensions, but when in terms of singular values, you don't really know what values are you increasing and decreasing. You don't know what trait to specifically those 10 values.
This is an astute observation, right? Which is everything I've been showing up to this point. When you say find similar, you're finding similar against that rich, complete embedding, right? All 512 floating point numbers. In this case, I'm using a little bit of a trick, which is saying, hey, this thing here doesn't have a reverse. You can't. It's like a one-way function, right? You can't reverse out to, oh, here's what the full embedding for this would have been, right? There's not an easy way to do that, or at least I don't know of one. So when I'm saying find similar, I'm actually comparing it against the PCA reduced dimensions. I'm again using the Facebook AI similarity search library. I'm just using it against the 10 dimensions as opposed to the 512.
So in regards to the question that was posed earlier,
yeah,
you wouldn't have any specific control on the traits of the sunglasses, whereas you mentioned the bridge between the two different whatever.
Right.
And so you can't really control what features you want to be similar, right? They would just get you the top 10 features that actually cause the variation.
Correct. And we don't know what each of those dimensions means, right? We kind of infer, like through trial and error, we figured out it was sunglass, non-sunglass. We figured out it was black versus non-black. I don't know what this third dimension is, right? Part of the reason I built this, and I admittedly, I built this a couple days ago. I haven't spent a lot of time exploring this. Ideally, I hooked this up so that the changes are both live and it's easier. Like this looks kind of cool, but it's actually kind of clunky to work with, right? So if I can figure out a way to say, oh, imagine I just kind of slid this control up and down, and then I can see what impact it has on the glasses. Or start with a real pair, and then it could show me, hey, if you went up 0.1 or down 0.1 on any of these dimensions, here's the glasses you would have gotten to, right? Those are things that I'm interested in exploring. I haven't gotten to that yet. Yeah, go ahead.
So is there anything that can help with explainability, or is it just a black box until someone figures out how to solve that problem?
I don't know. I don't know. I don't know if there's my hunch is there's not. Really what you're saying is you have unknown binary data going into an embedding system. We then run PCA on it, and then we try to infer back what caused the variation based on the images. I don't know that there's going to be an easy answer to that, other than we as humans are pretty good at picking out patterns. So look at a bunch of data, and then we start to figure it out. Just trial and error. I think so. Yeah, I think so. Yeah.
So that I understand this, the 512 dimension data set in the beginning,
yeah,
before you reduce it to 10 dimensions, that I assume that those data points are very defined. Okay, so like one data point in that one dimension in that array, okay, will be like the total length of the glasses, let's say. Okay, but then the 10 dimension,
yeah,
the 10 dimension set that we don't know what that automatically reduces it.
Yeah, so with the 10 dimension one, because you're using principal component analysis, it's kind of like saying, well, this second dimension value is a combination of array elements 3, 17, 24, 25, and 74, right? And then where does that leave you? Yeah.
Easily for this.
Okay.
And clustering them, and on the basis of that, you could, it would help in the trial and error to see what dimensions are pointing to what trait. So if you get a three-dimensional t-snake plot with it, and then you play around with it, you could actually, point out to some extent what features are clustering together.
Great. Let's talk afterward. I'll take some notes on that just to make sure that I've got the right context on it. The last piece of what I did, and Ita, how are we doing on time? Doing great? Okay, good. The last piece of this is, so there was a mention earlier of, oh, I know the OpenAI clip model. Clip combines images and text, right? And so really what it's doing here is it says, okay, so if you have text like the word cat and the word feline, they're going to map to similar space and embedding space. However, if you have the word cat and a picture of a cat, it's also going to map to similar space and embedding space, right? So what did I do? I said, okay, well, if that's one of the properties of this model, let me add a text search box to the beginning of what I've done, and then I'll display the results with these visualized embeddings. So an important thing to keep in mind, I didn't provide any metadata for the glasses images. I didn't provide shape, I didn't provide color, I didn't provide size. I only gave it binary data, ran it through embeddings. Do we see what it does? Okay. So I search for Aspen, Colorado. I know, it's weird, right? I search for Aspen, Colorado, and it returns ski goggles. How wild is that, right? So there's something in there of, something about Aspen is triggering, oh, it's sort of ski-ish, vibe-ish something that then is mapping back into, well, glasses that are ski goggles also land in the same embedding space. To me, this is mind-blowing, right? Like, how can that possibly be? The next one I did was Eli Manning. You guys all know who Eli Manning is? So look at the glasses that it returned for a search for Eli Manning. It returns NFL branded New York Giants sunglasses. Next, I search for cheetah, right? So when you search for cheetah, what do you get? Right? Here are a bunch of glasses. Oh, wow. But I did not provide, I did not put the description in the system at all. No.
But the description of the glasses, it's not just, the description of the glasses for that product, okay, probably described as a cheetah frame sunglasses or something like that, I'm assuming.
Yeah, I mean, that's if what Clip is doing is it's saying, hey, I'm training on a lot of data, right? And if this or something similar is in the training set, right? I think it's probably less about the descript. I mean, is it possible that the training set had enough data about glasses with a description with the word cheetah? Maybe that's possible, but probably much more likely is here's 100 pictures of cheetahs and they all have this pattern. So then now I'm using the word cheetah and it says, oh, I know what this, swirly colored pattern is.
Are these glasses still coming from the original 30,000?
This is, yeah. These are all from the original 30,000 database, right? Yeah. So other variations that I want to do here but have not done yet is, so when you have cheetah, what I want to do is I want to take that text, run it through the same PCA model, right? So that I can then get the color-coded embeddings the same way. Then once I have that, get to an equalizer type situation, right? Which, if I put in some random text, I then get, oh, this is what the equalizer looks like. And then I can start to, I don't want to use the phrase fine tune, that has a very specific meaning that is not at all related to this. But then you can start to play around with, okay, well, if this gets you close, how close is it actually getting you? A couple of comments about the bonus section. One of the things to keep in mind, notice the distance in Euclidean score. Like all the other scores were sub 5, sub 10. Here, this is like 130. 130. Like, these are actually pretty far. So that was one thing that jumped out to me. Another is I'm cherry picking a few really, really good examples. Not all of the examples come out as good as this, right? These were the ones, in terms of playing around with it, these were the ones that really popped of, oh my goodness, this blows my mind. I can't believe this happened.
Does it have an initial training on like Facebook, like billions of Facebook images, and then you're applying that same model to the 30,000, or
Yeah.
just on the 30,000?
So OpenAI's clip model, they built that in January of 2021, right? That's something they built a long time ago, and there's, in terms of the specific of what data set they used for that, I don't know if it was ImageNet or what it was. Yeah.
With Aspen, if 100,000 people geotagged Aspen on their photo.
I don't think geotags were a part of the, the way they trained that data, it was a combination of here's an image and here's some text, and then have those, basically construct it so that both the image and the text go to the same space in terms of embeddings, rather than paying attention to like other metadata. Yeah.
Yes, coming to this Aspen thing, right?
Yeah.
It might just be that Aspen is more associated with ski,
Yes.
for sure.
Oh yeah. I think that's exactly what it is, right? I think Aspen gets you, even Colorado, both of them get you in vibe space of skiing, and then ski goggles also are in the vibe space of skiing. Yeah. Go ahead.
You mentioned about them being large.
So what I was saying about the distance is, if you look at the distance numbers for everything we've looked up to this point, they've been like sub 5, sub 10, as in the glasses are really, really close to other glasses. Even though text and images are going to the same embedding space, they're still like, they're not nearly as close. They're significantly further away. The thing I haven't explored in that is, maybe they're really, really close in the first 10 dimensions, which captures 70% of the variability. And it may be that additional variability is like, way down in the long tail where you wouldn't necessarily notice. Yeah. So I'm not sure about that. Yeah. Go for it.
I was just curious if you tried some query text that was sort of closer conceptually, like a black pair of sunglasses with cheetah frame or something like that.
So some of the examples that I've done, if I put in a color, so like I put in Pink Panther, boom, everything is pink, right? If you put in color at all, it's very sensitive to color, right? So color goes through. The reason I didn't highlight color on this is because it's too easy to mentally think that that's a facet, and then it kind of gets you in the world of, oh, well, that's not really novel, because every search interface I've ever seen has facets, and color is a common facet, and therefore if you put in yellow, like, of course you're going to find yellow glasses. People tag them that way, right? But like sports heroes don't normally. Yeah.
I was thinking that maybe that would reduce the.
Oh, maybe that would reduce the
like
number.
If the word sunglasses was in.
That's a good question. I'll have to play around with that. I'll have to give that a try. What I have found, it's pretty uniform in terms of the minimum number. Like I haven't been able to get it below like 130, let's say, right? So I don't know if there's any meaning in that. Like, notice the closest ones, 136, 132, 138. I don't know if that means, oh, there's some, text and images are close, but they're not that close. And then they're like, yeah, like, the movable dimensions at the beginning are all really tight, and then there's something in the long tail that's causing it to just be uniformly wide. Yeah.
Yeah, I think just similar to what he was saying there, again, if you had like the query text about glasses, I think some of that 130 might just be how far glasses are from the average text.
Yeah, it could be. It could be. Yeah.
Because it's interesting. It's notable how even though it's 136 away, all the other ones are very close to it.
Right.
So it's like that's
Yep.
where it starts. There's like 136 of like, and all of the ones you did are all the 130-ish away.
Yeah.
So it's just notable. The other thing I think was interesting with Eli Manning is the top two. I think even though the top 5 are probably all NFL branded,
Yeah.
the top 2 are blue, which is the Giants color.
And you also, so if this is way too small for you to see in the back, but it's New York Giants, and then this is Ravens, Seahawks, Ravens.
So is it, and then is that coming in from, that's all coming in from the image, that it's noting that there's an image of the Giants there?
I believe so. I believe so.
Did you try to see the distance if you just put the word glasses?
No, I'm going to try that. I've not done that.
I mean, that hypothesis can be tested. You could
Yeah.
just crop out that part.
Yeah.
Oh yeah, and run it again. Another thing I'm looking at in terms of, hey, where would I go with this project is, and this was based on a conversation I had with a friend this past weekend, was he was saying, this is great because I have this pair of glasses right here. I have no idea who the manufacturer was. I have no idea who made it, but I want to find glasses that are similar to this. Can I set them down somewhere, take a picture of it, and then use that picture to find similar glasses against my similarity set? Of course, my reaction was, oh, that's a great idea. I haven't built it, number one. Number two is, yeah, I can probably build that. Number three was, one of the things to be careful about in a system like this is because notice a property about these 30,000 pairs of glasses is that all of the glasses are professionally photographed in white background. I mean, they're all beautiful pictures, right? These pictures are just stunning in terms of their regularity, right? So if you then say, and actually the example, so what Drew did, the thing I was building off of what Drew had done is he did something similar to this, but with faucets. He was trying to use, hey, can I build similarity search for faucets? But what he found was the images he had scraped, they were kind of all over the place, right? Some of the faucets were on a nice white background. Others were in New York City apartments, where there's a lot of other stuff going on. So he had that as, yeah, this kind of worked, but it didn't really work. And here are some of the reasons it really didn't work. So my starting point for this was, can I find a data set that is pristine where I can just kind of bypass that problem? Right? So I don't wear glasses. I don't have a particular thing about glasses. It just happened that glasses are an easily scrapable data set. Yep.
Just an idea, would running it through like a background removal work for that as well?
So so I actually, yeah. So one of the things to notice in terms of background removal, if you look at this, notice here these images. I did 200 images, but they start to, like, the corners start to overlap on other glasses. So I was originally playing with, oh, let me put on 1,000 glasses, but then the corners overlap so much that it becomes distracting. I then said, okay, well, let me write a Python script to call the rembg package to remove the background on these images. Turns out it takes 10 seconds per image, which is 4 days of my computer sitting running. So I did that. I paid the 4-day penalty, and I figured, oh, I'll go ahead and do that. What happened though was the remove background algorithm for the glasses on the left-hand side, about a quarter of the time, it would take the clear glasses and make them sort of grayish in a certain way. So that I waited 4 days for this data to come out. I got it. I'm gonna load it up. I load it up. I'm like, yo, no, what happened, right? So I'm gonna look for alternatives for that, because I think it'll pop a lot more if these things aren't overlapped, right? So not directly. I know you were talking about something else differently, but I was using that as a way of, hey, instead of having a JPEG, can I flip it to PNG, drop the background, and then visually it'll be kind of easier to see these things.
Well, I'm saying for the new picture,
Yeah.
if somebody were to take a picture.
Yeah. Okay. Yeah, that's. I'll say it, and you can tell me whether I got it. Which is the case of, hey, my friend's got some pair of glasses. Oh, you can just take a picture of it. Maybe they're. I could say, yeah, if you want to have good results, make sure you take it roughly like this, and it could even be a template or white background or something. Or maybe I could do some image manipulation, right, of detect its glasses, white out everything else, go from there. Yeah, it's a good idea. All right. Any other? Okay, so that's that's it in terms of bonus content. Yeah, go for it.
All right, so this is going back to the idea of finding directions in the latent space where you want to manipulate like the bridge of the.
Yeah. So it's a little bit of, hey, maybe it's something related to the equalizer. Yeah.
Because if you can find a pair of glasses that are very similar, except the bridge is very different.
Take the
And-
two and
yeah.
look at the
Look at the
PCA.
delta.
Yeah.
Without doing the PCA. Just
Oh, okay.
From the original latent vectors,
Mm-hmm.
you get a delta latent vector
Yes.
that you can then
Yes.
apply with some scale factor
Mm-hmm.
before doing the PCA, run it through, and then find the similar glasses to that point. This
Interesting.
only works.
Yeah.
This only works for features where you have pairs that are far apart in one thing that you're interested in.
Okay.
It's similar in everything else.
That's the word to example, right? Man minus woman plus.
Yeah. There's some great examples. Like, oh, you're at Paris. Like Paris minus France plus Germany is Berlin. How on earth? We're just talking about word-to-vec and embeddings. Yeah, you can do embedding math, which is kind of wild, right? So what I'm taking away from that comment is this concept of embedding math. Maybe you can do that if you have two similar pairs of glasses that differ in a very specific way, right? Yeah. I probably the single biggest way that two pairs of glasses would differ would be the color, right? Hey, here's a black pair, here's a blue pair, here's a red pair. It's the same glasses, right? They just happen to be colored differently. That's an easy one to pick up. Okay, well, what's the model doing, right? But why not do it with the bridge? Why not do it with this? Yeah, I like it. Thank you.
Oh, did you use like Scrapey or Beautiful Soup?
I use Scrapey. Yeah, I use Scrapey. I did not for this project. I didn't use Beautiful Soup. I did use it for other LLM similar.
But for a lot of images, does Scrapey work well?
I found that I used it. So I used Scrapey to get all of the HTML files down on disk and just, okay, great. Now I've got 30,000 HTML files. And then I went through and I said, let me parse each of those to find what the URL for the image is. And then I just I think what I did, this is the very first thing I did. So I'm trying to remember what it was. I think from there I said, let me just write a Python script that can rip through a bunch of files, look, in a certain spot, find the URL, go download that, item. Yeah. So actually, I probably did use Beautiful Soup to get me kind of in there. Yeah. I thought I've done it for other projects too, but probably I did it there as well.
Can you describe an application of this for looking for patterns in, let's say, network logs for computer security?
Can I describe an application of looking in like specifically the equalizer, or just this whole project in general?
Like equalizer. Okay, I want to let's say you have a lot of packets and you have some anomalous behavior, but you want to find similar behavior in other packets, or you want to see something you can so that's something that you can determine a common theme among all these packets.
So I've in terms of my own background, right? I've spent 17 of the past 22 years working in network performance monitoring, and another 5 years in security. So I should be able to answer this question. I can't. Nothing jumps out off the top of my head. I'll have to think about it a little bit more. I mean, the kind of the key takeaway in all of this work is okay. So it's all about the embedding and similarity search. That similarity search is the exact same concept. Like it's the exact same thing as retrieval augmented generation, right? So I think where you end up is, if you're trying to find similar things in log data or really anything with text, you're in the same zip code as all of this. I don't know yet where, oh, if you're PCA reducing a random set of text, then if you start moving one of the dials on one of the dimensions, like I can't crack that. Yeah.
I was just going to show, so one thing that we've done with embeddings was looking at logs for builds. So for build logs that have errors in them when we're doing like mass code migrations, we have thousands of build logs. And we fed them into an LLM to get a summary with a prompt that sort of said, ignore these kinds of errors and focus on these kinds of errors.
Yeah.
And then we fed the summaries into an embedding model and then clustered to sort of see, okay, what are the biggest categories of build failure, so we can focus on fixing those. So that's kind of a similar application.
That's really great. So take a look at Simon Willison is the guy that I mentioned earlier. He built a package called Dataset, which I built this thing on top of, and then he also has something called LLM, which is a plugin for Dataset that can do a lot of interactions with LLMs. And one of the examples he gives is very similar to what you described in terms of clustering, right? So I'm doing things that are similar to like LLM similar. He had some things of LLM cluster where I think he ran all of his Python code through an embedding model and then had it cluster out. I think it was like GitHub issue names or something. He then had a cluster, and then he had the LLM generate summaries of those different clusters. I actually looked into doing it for this, but because I don't have any metadata anywhere, you kind of lose the, oh, it's image 1, 2, 3, 4, 7, right? Like, what do you do with that? But that may be another way that I could take this of, okay, now that I've got things clustered, which it can do, then can I don't know, take representative samples from that and pipe it back, or maybe I end up inserting metadata into it kind of from the beginning. I don't know. There's a couple different ways I could go with it, but it sounds like it's similar to some of the things that he's done. So check that out. Yeah.
So this may be a dumb question, but actually I saw Simon Williamson like 2 weeks ago.
Oh, did you really? I've been
He was the keynote, right?
in Pittsburgh.
I did.
Oh, that's excellent. Yeah.
He's a very bright guy.
Oh, yeah.
Yeah. My question is, how are you? In the keynote, he was saying that with LLMs, one of the big things that you have to do is think about the verification, validate the results. Is that something that you're thinking about?
So for this project, this is all based on embeddings. So because of that, I'm not landing in the same space that he is of, hey, I had an LLM generate some output, right? This is really just taking advantage of fundamental technology. So yeah, it hasn't been a concern. Yeah, there's nothing I've had to worry about there.
So, in this same topic of
Yeah.
embedding-based similarity search or not, are you familiar with the image bind model?
Image bind? No,
It
tell
came
me
out
about it.
a year ago.
Okay.
It's based on clip.
Okay.
They took clip, froze the image part, but they mapped into it text, audio, thermal imagery,
Oh,
video as
interesting.
well.
Oh, really? So
you
they
can
loaded
do-
it up with a bunch of things. Okay.
Yeah, so you can do lots of interesting things. So you could take like a picture of a person and map it to like a sound. Like
Okay.
what that person might sound like.
Uh-huh.
Uh,
That's wild. So it's called the image bind.
image.
Okay, yeah, I'll definitely have to check that out. Yeah, because I mean, if you look at it, OpenAI's clip model came out in January of 2021, right? It's actually in the world of this stuff, it's relatively old. And I know that there have been some additional enhancements on the clip model, but I wasn't familiar with image bind specifically.
Okay, yeah, I had a question about.
Yeah.
So what's like the feature thing in the PCA? You said something about like it having 70% capture and 70%.
Yeah.
Okay,
Mhm.
why was that just like arbitrary that you showed me like 10, 70%?
It was so what I did, like, why did I choose one versus another? It was really arbitrary in terms of picking 10. I wanted something that I didn't want to pick 100 because then I felt like it would be too skinny and you wouldn't actually be able to see these bars. If I only pick 2, that gives you, well, that's a bad example. If I pick 2, that gives you this on the XY dimension, right? But that only captures like 45% of the variability. So I felt like I had to go a little bit further than that. I kind of played around with it, and if you get to, forget the exact number, but 10 got you to 70%, and then at some point it flips you to like 95%, but that's like 50 or 70 or something. Yeah. So I mean, a little more art than science on that one. All right. Anything else? Yeah. Go for it.
Where do you hope to go like further with this?
Well, I mentioned in line a couple of the things of, if some examples are the text search part. I want to see what text does in terms of these colored histogram, like the PCA 10 thing. I want to figure that out. I think that'll help me understand why the distance is so far away on these like bonus examples, right? That's one thing. I think a second one is I'd love for the equalizer thing. I'd love for that to either, it's not quite right. It's too clunky. I want to play around with that. Maybe end up having an updating live, or come up with some sort of display that gives you hey, if you like this pair and you want to modify in one of those 10 dimensions, here's what that step would look like, right? So it's kind of like, choose your own adventure. You're here if you wanted to walk in one of 20 directions, if you want to call it that, 10 high, 10 low. If you were to do that, here's what the next closest pair of glasses looks like. That starts to get into the intuition of, well, dimension 3, what is that controlling? I don't know. Let me walk in that dimension and keep going, see what it says. Okay. So again, I haven't done that yet, but those are some of the places I want to take it. More broadly, this is really all foundational stuff for, it puts you right in the orbit of retrieval augmented generation.
Okay, well, if there are no other questions, let's give our speaker a round of applause. Thank you.
All right, thank you so much. And again, here's my contact info. Feel free to take a picture of that. Do reach out to me after. Yeah, happy to talk about this and other stuff.